All righty, folks. How we all doing? Good to see you guys. Good to see you. So we're going to continue moving through. We spent a little bit of time now dealing with derivatives and integrals of natural logs, and we talked about inverse functions. So if we think about the inverse of a natural log, then what we're really looking at here is when we have it change its form. So if you remember right, that e is the base of the natural log. To figure out that inverse function, we just switch our x and our y and solve for y. So e to the x equals y. So this e to the x function is the inverse of the natural log function, which we knew. We talked about in Algebra 2/Integrated 3. We've talked about it in pre-cal. But just now it's time for us to deal with it from a calculus standpoint. So let's let f of x be this function e to the x. And it's good to remember what e is, all right? It's that Euler number, but that e comes from this idea that, or not idea, it is derived from this limit as n approaches infinity. 1 plus 1 over n is equal to n. It's also derived from that value, that limit. And again, we talked about this a couple days ago as well. This is how our good buddy Leonard Euler decided to come up with these values. This value of e comes from this limit as well. Just another way to rewrite essentially the same thing. So this is that value that we're talking about here. So say I wanted to know what the derivative was. Let's take it back to the definition of a limit. And I'm not going to use delta x, I'm going to use h. So as h approaches 0, we have f of x plus h, so x plus h, minus e to the x all over h. So this is the one that we're currently dealing with here. Now, if I'm looking at this thing here, I kind of notice that this e to the x plus h, I can rewrite that. So h approaches 0. We have e to the x times e to the h minus e to the x all over h. So if I do a little bit of factoring here, I find out that I can take that e to the x out, and I'm left with e to the x times e to the h minus 1 all over h. So now this is the time where we have to get just a tad bit creative here. And what I mean by that is, let's go to this limit. What if I take this limit and I raise it all to some exponent? If I were to do that, just for the fun of it, that would be e to the h. So there is a way that I can make this e to the h pop up. Now, if I take a whole limit to an exponent, that's the same thing as just taking, oops, that was an h. I meant to take that to the n power. Sorry about that, friends. Let me quickly erase here. Quickly. There we are. So let's take this all to the n here. Then we get e to the n as n approaches 0. I can take that right here and just bring just the expression to the end. So I have 1 over n to the n. And if I have an exponent raised to an exponent, we've said to multiply it. So e to the n is the same thing as the limit as n approaches 0 of 1 plus n. So what if we just, because n is just a random variable, what if we let n be equal to h? Now all of a sudden we would take this e to the n and that would become e to the h. So the limit as n approaches 0, now that would be h approaches 0. So we're just taking Euler's limit definition of e, and we're just kind of playing with it a little bit. Now in place of 1 plus n, I have 1 plus h. And by doing that, friends, I think I see an e to the h here now. And I bet I can make a quick little substitution here. So in place of e to h, how about I plug in 1 plus h? Because that's what these essentially equal. If it's a limit as h approaches 0, which this is. So if we do a real quick little substitution in here, since I'm dealing with a limit, and then we keep going here, I think I get those ones would cancel out. You get e to the x. The ones that cancel out, I have h on top. I have an h on the bottom. So then I'd be left with this e to the x. And since I don't have an h to plug that 0 into anymore, it turns out the derivative of e to the x is actually c to the x. And I don't know about you folks, but I find that kind of cool. Its own function is its derivative. So the derivative of e to the x is e to the x. Well, that's kind of cool. And if we take it a little bit further here, we can plug a f of x in for that function, in for that exponent. So let's make that e to the f of x. That derivative is e to the f of x, so it's still the same thing, but we're going to multiply it by the derivative of that exponent. So this is what we're playing with today. We're going to be playing a little bit with this derivative of e to the x. And then next week or next class, we will deal with the integral of e to the x. So we got the time this year, so let's go ahead and use the time. We don't have to try to do it all in one day like we've done in the past. We can do it in 2 separate days. So let's throw some functions up here. What I want to know is find the derivative of the following functions here, friends. To determine the derivative would be help if I could spell here. Determine the derivative of the following functions. There we go. And let's just throw a few of them up here just for the fun of it. How about let's try f of x equals e to the x plus 4. Let's do f of x equals e to the 3x minus 1. Well, how about f of x equals e to the tan x? And f of x, we're just going to do a few derivatives, and we'll do a couple applications, and then we'll call it a day. We're going to keep today pretty straightforward. X squared minus 1. All right, so here we go. We're not going to overcomplicate this. To figure out the derivative, all we're going to do here, friends, is you keep the same function, so that never changes, and then you multiply by the derivative of that function. So x plus 4 is just 1. So f prime of x is still e to the x plus 4. Okay, with that in mind, I want you guys to go ahead and pause the video and see what you guys can come up with on these next ones. All right, so our first derivative. Let's see how you all did here. We keep the function, and then we multiply by the derivative. So 3. So the derivative would be f prime of x equals 3 e to the 3x minus 1. How about this one? F prime of x equals e to the tan x and then I'm going to multiply by the derivative of the exponent. So the derivative of tangent x is secant squared x. Or secant squared x times e tangent of x. All right, last one. Now, hopefully you guys did this first. You rewrote it as x squared minus 1 to the 1/3 power. So derivative, we just keep the function. And then we multiply by the derivative of that exponent. The derivative of that exponent, which would be 1/3 x squared minus 1 to the negative 2/3 times the derivative inside. I got to do a little chain rule on that one, times 2x. So if I just rewrite this to try to get rid of everything and make it clean again. So we have that e to the, oopsies, got my 2x there. I have 2x times e to the cube root of x squared minus 1 all over 3 times x squared minus 1 to the 2/3. Or you could say the cube root of x squared minus 1 squared. So hopefully this isn't too terribly bad. You're looking at this going, okay, it's pretty straightforward, not too shabby. We'll try a couple of applications here of it, and then, like I said, we'll call it a day. Determine the equation of the tangent line to f of x equals 3e, I'll give it an exponent here in a second, plus 4x minus 1 when x equals 0. Use the tangent line to approximate the value of f of 0.1. All righty. So what exponent am I going to give you today? How about I give you, friends, sine of x? Not going to be in green, though. Okay, so to get the tangent line, first of all, I need to evaluate. Oops, I forgot to tell you what value we're doing this for. Value x equals 0. So to get the tangent line, well, actually pause the video, take a shot at it, and then we'll talk about it. All right, here we go. Did you actually pause the video? I wonder sometimes. The first thing we got to do is got to figure out the y value that's associated with this, and then we will go through and deal with the derivative. So if I plug 0 in here, I find out that f of 0 is 3 plus 0 minus 1, which is going to be 2. All right, so the point that we're dealing with our tangent line at is at 0, 2. We just need to know the slope, so we deal with the derivative here. So we have our function 3e sine of x times the derivative of that exponent, which is cosine of x, plus 4. And the derivative of -1 is 0. So we're going to evaluate this here for 0. I guess that 10 equals 1 right there. And when we do the derivative here, we get 3. There's that one that I just wrote back on the other one, because it's kind of trivial. Anything to the 0 exponent is 1. And another 1 from cosine is 0, and plus 4. So my derivative would be 7. The derivative value at 0 is 7. So f prime is 0, 7. So that'll be the slope of my tangent line. So here we go. Tangent line, y minus y1 equals slope times x minus x1. So there's my tangent line. And now I'm supposed to use that to evaluate for the value of 0.1. So first thing I want to do is I want to get y by itself here. And x minus 0 is x, so I can just make that 7x plus 2. And we are going to evaluate this for 0.1. Now, this is a linear approximation, so we want to make sure we put the approximate symbol here. And when we evaluate this, friends, we end up with 2.7. There we go. All right, so we can still play with this and do all our normal application type things with it in general. Let's try one more thing just for the fun of it. Determine all the points of inflection and relative extrema to the function f of x equals x e to the x. All right, so haven't done it for a while. It's time to go back. We're going to say what we're going to do, then we're going to do our work, and when we're done, we'll say what we found. So here we go. Let's say what we're going to do first. Relative extrema can exist when f prime of x equals 0 or when f prime of x is undefined. Points of inflection can exist when f double prime of x equals 0 or when f double prime of x is fine. All right, so I gave myself permission that I'm going to go ahead and play with the first and second derivative and what I'm going to do with it. So now we can go ahead and do that and see what we find here. So let's deal with the first derivative. So realize this x e to the x. Don't be confused by that. Technically, that is x times e to the x. So I'm actually dealing with the product rule here. So f prime of x, I have my first times the derivative of my second derivative of e to the x is e to the x, plus my second e to the x times the derivative of my first. And if you notice here, I have e to the x on both terms. So what if I were to just factor it out? First, let's just go ahead and rewrite it. X e to the x plus e to the x. And what if I just factor out that e to the x? I would have e to the x times x plus 1. So set it equal to 0, and let's see if we can't find these critical numbers. Well, e to the x is an exponential value, so that will never, ever, ever be equal to 0. It's always a positive value, no matter what the value of x is. But I do have one critical number here. So x plus 1 equals 0. So x equals -1. Well, let's go through now. Let's find out, does it change? Does the value of the derivative change at x equals -1? So I'm going to pick a couple of values that plug in here. How about x equals -2 and x equals 0? When I plug these in here, what do I get for my first derivative? Is it a positive value or is it a negative value? Well, on this side, I would end up with a negative value. So that's less than 0. If I plug 0 in, I'm going to get a positive value. That's greater than 0. So if my derivative changes from less than 0 to greater than 0, that means at x equals -1, I have a relative minimum. I just need to know the y value for that. So let's go figure that out real quickly. What is the y value for that relative minimum? So I have -1 times e to the -1. So that y value, oopsies, is -1 over e. All right, so now I know that I have one relative min. What about a relative max? Do I have any of those? So let's see here. I'm going to start with that, not relative max. I don't have any relative max. What I meant to say was, do I have any points of inflection? So plus e to the x. There we go. So we're going to have to do a derivative again. And again, I have a product rule. We've already done this one, but just to kind of reiterate what's going on there, I have first times the derivative of the second plus second times the derivative of the first. And then I have this extra e to the x, because the derivative of this e to the x is just e to the x. So if we clean this up a little bit here, I have x e to the x plus 2 e to the x. Why did I make that e to the x in the exponent? That's the question. There we go. So just like before, let's factor out that e to the x here. And we have e to the x times x plus 2. Set it equal to 0. And again, e to the x is always a positive value no matter what I plug in for x, so this will never be equal to 0. But x plus 2 does give me a critical number. And that would be at -2. So just like before, we're going to test that value and determine, do we have a change of sign for our second derivative? So I'm going to plug in two numbers here. How about x equals -3? I'm a big fan of 0 the hero. And that back in kindergarten with my 100-day project that I had to help my kids do, or keep doing. You'd take your pick. And let's see here. If I plug this one in here, I get a second derivative that is less than 0. I get a second derivative that's greater than 0. So I am going to have a point of inflection at x equals -2. So what I have to do then is I have to figure out what is the y value that goes with -2. So we plug it in here. F of -2 equals -2 e to the -2. So we have -2 over e squared. So that's my point of inflection. So we said we were going to do, we did all the work, and now, friends, it is time for us to say what we found. And I'm going to leave some spaces here because I'm going to have to go back and rewrite it here in a second. But it's going to essentially look like this. F of x has a relative minimum at, oh, what was that? -1, -1. I'll come back to that in a second. Because f of x, or f prime of x, changes from f prime of x less than 0 to f prime of x greater than 0 at x equals -1. And also f of x has a point of inflection at -2, negative, and I'll have to come back to this one as well, because f double prime of x changes almost from, or changes signs. I don't have to say how it changes. I just got to say that it changes signs at x equals -2. And now we go ahead and we clean this up a little bit here. So what point was this? This was -1 over e. And this one was -2 over e squared. F of x has a relative min at -1, comma -1 over e, because f of x changes from f prime of x is less than 0 to f prime of x greater than 0 at x equals -1. And then f of x has a point of inflection at -2, comma -2 over e squared, because the second derivative changes signs at x equals -2. Said what we're going to do. We did the work. And when we're done, we say what we find. All right, friends, that pretty much takes care of for today. Next class, we'll talk about the integral of e to the x and how that works. Talk to you later. Take care.